Okay, looks like we are back and everything recorded okay. So now I'm going to look at applying the same type of model that we used for the link budget for a communications problem to a radar problem and derive what's known as the radar equation. So to set this up, we've got very similar geometry as we did with communications, in which I'm going to have some antenna with the input power, and I'm going to have a target, my radar target. But what's maybe a little different in the communications problem is I'm now going to have a receiving antenna. Maybe that's similar to the communications problem. That's at a different location, and so I'm going to want to know what is the received power coming into my receiving antenna from my transmit antenna, reflecting from the target, and then reaching the receiver. Okay, so power in, power out, dimensions of watts in, watts out, express everything in dBs, but it's the same type of analysis we did with the communications link budget. And if you remember what we did in the communications link budget, we said, well, I have so much power being generated at the transmitter. All of it, if I draw this imaginary sphere around the transmitter that goes through my target at some distance, our transmitter, the area of that sphere is, and I'm not going to define a new symbol, I'm just going to write, the area is 4 pi RT squared. Okay, so the total integrated power crossing over that sphere has to be equal to the transmit power minus whatever may be lost in the space in between, say absorbed by heating the atmosphere or anything like that. And we're going to add a correction for that loss later. And if we design the system right, that loss should not be that big. Okay, so if we have a isotropic antenna, remember that term means an antenna that radiates power equally in all directions. Our power density at the target is the input power divided by the total area over which I'm illuminating, the total area that I am illuminating. This 4 pi RT squared, right? And so this will have dimensions of power per unit area. And in a radar, I may want to have something that's an isotropic antenna or close to an isotropic antenna because I don't necessarily know where my target is. So I might want to spread the power over a larger area and hope to see a reflection of the target. And we're going to talk about that issue later. For now, we want to maybe optimize the system a little bit. So let's say we've already detected where the target is and I'm trying to measure the range to it. So in that case, I'm wasting a lot of this power because if I've already detected the target, I probably know about where it is. So I can have a narrower beam of my transmitter and I can increase my power within a narrow beam and reduce it everywhere else. And in terms of the communications link budget, remember we expressed that as our gain. So if my gain is unity, I'm equally spreading my power over this sphere. But if my gain is larger than 1, I am focusing the power in a smaller area of the sphere. Okay? And so if you remember from the communications link budget, then we had this power density and we multiplied it by the effective area of an antenna. I don't want to use the same color. This power density here, and we multiplied it by an effective area of an antenna. And then we captured all that power into the receiver. But it's a little different here because what we want to look at is all of this power is going to hit my target, and that target has a certain area that's going to represent how much of this incident power is captured and then reflected from that target. So we're going to represent the target as being this ideal, perfect reflector with a certain area, and that area of the target has a symbol sigma, and that is called the scattering cross section, or the radar cross section, or RCS, and that has dimensions of area. Okay, so this is the ideal reflector. Now I drew this at an angle to the incident beam from the transmitter, but really it's an idealization. So I should maybe have written it as, you know, this perpendicular. So that's whatever that cross sectional area is. Now that's an idealization. So 100% of that power that's captured by the target of an ideal area of sigma naught is then re-radiated. So I now have a new source centered at the target that has a power of, and maybe I'll start keeping track of all this on the next page. I have my incident power density. Then I multiply by my radar cross section. So this is my power density in power per unit area. This is my radar cross section, or scattering cross section, in area. So the combination of these two has dimensions of power, and I can now think of my little target as a new source that's radiating this much power. And where's all that power going? Well, if I draw my imaginary sphere around my receiver at a distance r to the receiver, my power density at the receiver then is simply this incident power divided by the area of that sphere. So this will be my sphere. Sorry, my pen is not writing clearly. Sphere through receiver. So the product of all of these now, power, watts per unit area, is my power density at receiver. Okay, so the product of all of these at the receiver, my receiver has an antenna, and remember in communications we describe the antenna as having an effective area, and the effective area is an ideal area that captures 100% of the power density crossing through that area. So I multiply by my effective area, and I get my received power. Okay. One thing I want to include here, I mentioned it, is that this isn't going to be perfect. There is going to be some loss. So I might as well go ahead and include a loss here. And this could cover things such as some energy is going to be absorbed by the atmosphere. Some energy is going to be absorbed because the conducting, the cables and the conductors are not going to be perfect. All kinds of things. All that stuff is going to be looped together in a loss, which we hope is not too big if we designed our system well. And if you remember from communications, we had the reciprocity theorem that related the effective area to the gain of the antenna, where I define gain when the antenna is used as a transmitter and effective area when it's used as a receiver. But because of the reciprocity theorem, I can measure a gain from an antenna by using it as a transmitter, and that same gain would characterize that antenna's behavior as a receiver, and the relationship between those two, between effective area and gain, remember, was wavelength squared over 4 pi times gain, where this thing, this set of terms here, is known as the effective area of an isotropic antenna. Antenna has two ends. Okay, so let's plug all that in and rewrite this radar equation from beginning to end. So let's plug all this stuff in. So on the left-hand side, received power, and I have in the numerator, I'm going to have wavelength squared, receiving gain. I left out my transmitter gain. Yeah, I left out transmitter gain. That should also be in there. Transmitter gain, transmit power, radar cross section. All that stuff's in the numerator. So in my numerator, wavelength squared, transmit, receive, cross section, transmit power. All right, that's everything. Lambda squared, received gain, radar cross section, transmit gain power. Okay, denominator, I have my loss, 4 pi times 4 pi times 4 pi. So I have 4 pi cubed times my loss. Range to the receiver squared, range to the transmitter squared. Okay, let me double check, see if I got everything. Okay, I think that's everything. We can do a quick check of the units. Okay, wavelength squared as distance units. Gains are non-dimensional. Sigma also has an area units. Power. 4 pi non-dimensional. Loss non-dimensional. Distance squared. Distance squared. These would cancel out. I have dimensions of power. Everything cancels out correctly. Okay. Remember, it's not just a power that concerns us, it's the signal to noise. So I want to look at the noise power, and we're going to use the same model.